Alright, time for another DraftPhysics.com, debatephysics.com also. But nobody can make a argument, about the theory of physics and how the physics might work. They can't really do force diagrams and explain how energy moves through a system. Even when the system's fairly simple, they still can't do it. Won't do it. They'll just tell us smugly that you must believe in their truth. And the truth here under debate is the idea that you can make free momentum. That you can create a system where you put in a certain amount of momentum and you get more momentum out of the experiment, and you don't have to supply any energy. It doesn't use anything up. It doesn't take it from anything. Nothing loses its momentum to give you the extra momentum. Alright, and that's just not a real thing. You can't do that, frankly. You have to always account for it. And in this simple case, it's a pendulum. It's really just a matter of either you're doing this, that is, you have a piece of matter moving a velocity, or you are storing the energy in altitude, in the sense that you're pushing something up and going to get the energy back when you let it fall back to its natural position. So you've used velocity. You put velocity in, and there's two choices. You can keep the velocity, or you can lift something, okay, and store the velocity. And those two things, in my opinion, always have to be in balance in the case of this experiment. Now, as is usually the case, these people do these experiments, and they have what I would consider sometimes very glaring errors in them, and they don't bother analyzing their own experiments to see if they can find errors. They just, smugly state, oh look, I've done everything perfectly, and I've done everything to your specifications, and blah 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 blah. And it's just bullshit, because all you do is look a little bit and you can find the glaring mistakes. So in this case, there's a glaring mistake in the fact that Dispar, I made the point that, if you used a piece of plastic from a pill bottle or something that's consistent, you could put both weights inside the same shaped object, and that way they could go through the timing gate, and they'd be using the same trigger mechanism, and therefore you wouldn't have to worry about getting your times a little bit off. And so instead of doing what I suggested, he did something, his own little piece of crap, and it's an obvious piece of crap. Okay, so he takes a round cuff of paper, sticks it to one side of the weight, okay, and then allows it to go back and forth. And it's a piece of paper. It just doesn't have nothing's securing it to stay round. Nothing's forcing it to stay round, and so it doesn't. It turns into an oval, swinging back and forth. So you can see here, kind of obviously, that this dimension for this weight is substantially smaller than this big giant paper dimension for this weight. And this is supposed to be the lighter weight, of course. So, it's at least a 20% difference in the length across this distance, which, of course, isn't the same distance. 20% difference isn't the same distance. So, no big surprise you're not getting correct velocity readings. Alright, now for the rest of the experiment, it's also, he just didn't pay any attention. I make these arguments and they just don't pay any attention to them. So it's almost just a waste of my time to bother arguing physics, because they can't do that. And so you can sort of see here, he has a straight, again, piece of string forcing the two pendulums to be incapable of swinging outside of the limitations. So instead of a rubber band being between them that would itself stretch, or a loop of string that would go up and down, the energy has to move the pendulum over. So you're changing the angles at which the pendulums are swinging. So you can sort of just see from this image, if I make a straight line coming down here, you can't see that. If I make a straight line, see, this is the point where the pendulum is tied to this other point here, so you can sort of see that. And what's happened is that has shifted. So this knot has shifted from this center position to, 3/4 of an inch over. And so now the center of the pendulum is here. It's not over here. It's here. This is the bottom now, the new bottom. This is where the maximum velocity will be read. And that's if the pendulum is hanging straight down. That is, if there isn't a kink in it in some place, okay, that obviously makes the pendulum higher. So anytime you kink the straight line, okay, if I take a straight line and I put a kink in it, okay, I no longer have, this line is now shorter. This distance from the bottom to the top is shorter, and the more I kink it, the shorter that line gets, that hypotenuse. So I'm raising the object instead of allowing it to swing at its natural position. It's swinging at up a higher position, which means it has less velocity because it's now stored more energy in its altitude. So as it increases in altitude, it decreases in velocity. So I explained all this in the previous video, and he just ignored all of that. So, there's not much point in talking to these morons, about how the physics works. So, those are two. I'll do a little bit of drawing just to illustrate the point, but very flawed experiment, frankly, again. So yes, he's all, smug about it. Oh, look, it's 1.4, it's 1.4. They're always getting this 1.4 thing. And what that 1.4 means is actually a 50% increase in the momentum. So the momentum numbers in this case, he didn't do the experiment in the other case where the momentum is destroyed. So this is the case he did. The lighter mass. Okay, so to understand the paper collar thing he did, the weight is like that round. He put a paper collar around the weight like this. It doesn't touch except on one side. And so he didn't fill it with foam or do anything to make sure it stayed round. He just put it on there, and what's obviously happened is that paper cuff has just done this. It's turned into an oval because as it goes through the air, it's being compressed by the air and turning into something more air streamed. Kind of obvious. All right. So in this case, he's moving the lighter mass. So he goes in with a certain momentum. Let's just say it's 100. And this oscillates. And when this stops, and this has all the oscillation, his claim is it has 200 momentum. All right. No, 150. Sorry, my mistake. 150. Okay, so it'd be like 200 to 350. 300, yeah, 200 to 300 would be the same ratio. And that's more like his numbers, frankly. 0.2 meters per second to 0.33 meters per second, something like that. So a huge increase. A 50% increase in the amount of energy, okay, you now have in the system. You've made a 50% increase in what you started with, which is a bold thing. And then he says, if I do it the other way, that is, I initiate it this way, I'll lose 50% of the momentum. It'll disappear. Now, I'm obviously making the argument that the 50% is tied up in the mechanism itself. So if these weights only have two conditions, okay, the condition can be their motion this way, okay, and their motion this way and this way. And that's what you really have to consider, is that there's not just this velocity that matters. There's the position they are in gravity, which means something had to put them in that position, and the only energy that can put them in that position is the energy you initiate the system with. So any lifting has to use this energy. That can kind of, I think, be understood by a 15-year-old. So you really have to follow or trace both of those things. You can't pretend that if you are actually lifting and dropping the objects that you can just measure the velocity and that's all there is, because it's not all there is. And my simple argument is as the oscillator works, I mean, he does get you know, I had systems that maybe it would oscillate 5 times and then switch the energy, so we don't need to oscillate 5 times, make a complete transition from one side to the other. His is going something like 25. So it's taking 25 oscillations for the energy to move from one side to the other side. Which, you know, is probably a lot more than necessary. And again, it's because he's got this rigid, you know, tie between the two pendulums that is essentially just obligating them to move in unison. So if this one pulls, it has to pull this pendulum into this kinked dimension. Okay, so it's changing the length of this string. You can understand that if I put this kink in it, I have to raise this up. I have no choice. This object has to go higher if I have a bend in this string. So every time this string bends, I'm lifting the weight. And obviously if I'm lifting it, I'm going to be losing velocity. So whatever velocity I had to lose it if I'm going to be lifting the weight. So I think it can be understood that at any moment in this oscillation, I can find the energy in only one of 4 places. Okay, it's either in the velocity of this object, so that would be an arrow this way, let's say, or this way, or it's in the height of that object, and and the same for over here. So even though this might have 0 velocity, that is, it might be standing still, if it's standing still higher than it started, then it has stored a piece of the energy in that extra height that it's risen, and that's where the energy is, and you can't see it. I mean, you know, you can't see it overtly. You can measure it. I mean, you know, with enough detail of video, you could see it. Now, you know, he's got a pretty good camera, pretty good frame rate, so he probably should just do the whole thing in overview, and then do another image of the experiment close in, you know, where we can watch the pendulum swing, and we could even do frame rates, and we can measure how high they go, and all those details. Because I would argue at any one moment, okay, there's only the momentum you started with, and that's all there is. Okay, at any one moment, it's in this system, and you can't make 50% more. You can't make any free momentum. All right. What else is there to say? I think that covers that argument. So like I said, if you know, there's a point where they're both swinging 50% of the energy, you could say, is in one half and 50% is in the other half, you know, and then it goes 100% in one side, 100% in the other side, and keeps migrating through those conditions. And at every stage, you could say that this, you know, 75% of the energy can be over here and 25% over here, or vice versa. But it's always going to be 100% of the momentum has to be accounted for. I think if you just asked a physicist off the top of his head, does he think momentum is going to be conserved in this coupled oscillator, I think they're going to answer, well, it should be. And then it gets more complicated when you challenge them and say, well, what about kinetic energy theory? Because it just demonstrates that the two theories just aren't compatible. Either you have to destroy the momentum or create free momentum, or you have to destroy kinetic energy and create free kinetic energy. There's really no option. One of them has to break for the other one to survive. Only one of them can survive this experiment. Just a fact. And I'm clearly going to defend the idea that the momentum, as Professor Lewin would say, is the stronger one. If nature has to conserve one of them, it has to conserve the momentum. It can deal with kinetic energy one way or the other, but it can't finagle momentum. You don't really need that. Okay, sorry about that. Yeah, so I don't know if I'll go in any further. I think I've made the points that this experiment still isn't good enough. Okay, he's getting his 1.4, his magical 1.4 number. Alright, but he's getting it because he's made some errors. And we just have to wait for those to be fixed. you know, and realized. You know, I did talk about the center of mass also, and he sat there and just showed the weight and said, look, the center of mass is here in the center. Well, first says you. They have these pedestals on them. The little weights have extensions on them, so their center of mass is going to be somewhere higher than halfway. Anyway, and the point of it is to mark the center of mass, to have a spot that can be seen, visually seen, so that it can be, the video can be played in slow motion. We can see exactly if that center of mass is actually rising up and down, indicating the storage of the momentum in gravitational potential. But anyway, it's the same old bullshit. You know, they do an experiment and then they force me to dissect how they cheated it. And he even called he said coupled oscillator test number 3, more crap or more cheat, was both crap and a cheat. I mean, the cheat part is frankly, why couldn't you just look at this and realize that, hey, wait a minute, this doesn't look the same size as this. No, that's way off. Okay, it's fucked up. You couldn't do that? I mean, you couldn't see that this is nowhere near the center and this has probably gotten compressed, and yeah, that's way off. You couldn't see it? Alright. So anyway, you didn't look for it. I guess that's the obvious fact. And again, he said he had rubber bands. That's what this little refuse here is. This is refuse from a rubber band. And that's another thing you should have marked. You should have a little piece of paper, a little piece of tape, so we can see where the pendulums are hanging from. And we can see that the point at which they're fixed up here on the rod, you can't see that. It's up here. It's at an angle. So this is a decided angle here. This isn't vertical. It's on an angle, and that's a problem. Again, because if this string has an angle in it, then that means this weight has to be higher than it should be. It's higher than it would be if that angle wasn't there, which means it has potential it's not using. When it's swinging, it's not using the potential because it's higher than it should be. Okay. So anyway, its peak velocity isn't going to be where you have this timing gate, because its peak velocity is going to be where the string actually goes straight again. Alright. Let's see if there's anything else I got to say. Yeah, no, that covers it. It's just the same old shit. So, whatever. Again, I'll have to do these experiments myself, and then I'll oblige them, to find my mistakes. But hopefully I won't be making as many as them. Because I learned that, the truth is that all of these experiments do have a catch. Okay, I thought coupled oscillator, how could they fuck that up, right? It seems kind of a simple thing. You say the words coupled oscillator, what's so complicated? But it actually does make a huge difference, okay, how you couple the oscillator. And so we've gotten 2 examples out of him. I gave the example that I used that looked pretty good to me. Alright, so I used an example where the 2 are coupled by a very loose coupling. So it doesn't put much tension, okay? And this, if you put a little bit of weight on it, this goes up and down essentially to put the extra pressure on. So you never really kink the pendulum, okay? It never kinks. They stay pretty straight, and they're just putting a little bit of tension on each other. And as the rubber bands expand, the tension is in the rubber band. The tension isn't in bending the pendulum. Bending the pendulum is essentially a way of creating more tension. It's hiding the tension in this bend that's being created. Alright, that's a point that can spring back. Okay, and you really want the spring in here. You want this to be the place you store the energy for a very short time before you give it back and forth. You want it to go through here. You don't want it to be in the pendulum itself. Okay, so the two examples he did were, one example was really bad in the sense they had him tied at very strong angles, so there was no doubt that you were shifting it this way and that way, and the whole system was moving. And now he's corrected that in the sense it's not nearly as bad, but it's still bad in the sense that he now has something still very rigid. So this side can't possibly go this way without forcing a bend in this pendulum. So it has to do this for this to go over here. So every time the pendulum swings over this direction, right, to do this, it has to kink this other side, and it has to lift this weight. So that's not what you want. Alright, so now it's enough of the video. Till next time and such, blah blah blah. Been there, done this, over and over, and such.